Good afternoon, everyone. It's my pleasure to introduce our TSVP speaker for this week, Professor Andrés Concha, who is visiting us from Universidad Adolfo Ibáñez in Santiago, Chile. So we have a history. Andrés and I were postdocs in the same lab. I used to wake up at 1 p.m. and get to lab and work until 5 a.m. and then have breakfast and go to bed. He would work from 8 a.m. to 4 p.m. and then go home and then come back at 10 p.m. and then work until 3 a.m. So the first time I met him, I thought I was already weird. And I was surprised to see someone who was weirder than me. This gentleman here, he solves every problem in quantum field theory and then takes the classical limit. So he's going to tell us a story about playing with magnets, geometry, and bacteria. I'm assuming, I can't guess. I'm assuming it has something to do with magnetotactic. Okay, so without further ado, our TSVP speaker, Professor Concha. Thank you.
Thanks, Mahesh. Thank you for the TSVP program. Thanks, Lynn. Thanks, Jonas, for helping me with all the work. So today I'm going to tell you how a study of classical magnets evolved in a couple of, I would say, in a decade, and how I was collaborating with different people. And the main goal is the following. The main goal is the following. Is to know why I do this. First, there is an academic reason. The academic reason is that magnets are quite interesting. So from the one-dimensional Ising model to the solution in 2D, Onsanger solution, they're interesting. And you use in your fridge a magnet, you can use in your experiments, magnets. So they're everywhere. There is a second reason that it has to be with academic life. I was doing my PhD while Peter Schiffer did a beautiful experiment with his group when they, for first time, they produced lithographic frustrated lattices. So they were able to see some phenomena at the nanoscale. Perfect, some magnetic phenomena, and they were able to build that setup and those samples. And then Castelnuovo and Mosner, in a beautiful article, they show that in pyrochlores, in a specific type of pyrochlore, the excitation, so when you put some temperature, what is changing look like magnetic monopoles. So there was a nice mapping there. And I wanted to see what, out of all of that, there was something simple, something that we can learn from classical mechanics. At the time, it looked like a stupid question because this is all quantum materials. But then we will see if it was a question. I won't say it was the best, but not the worst. So that's the reason why. Then I'm going to introduce a model that's called a dumbbell model for dipoles. Essentially, think as a dipole as an object that has a north pole, a south pole, but I'm not going to consider a point-like limit. They are finite, and that's important. That's going to be very important. Then I'm going to show you a two-dimensional experiment when we mimic the experiment in Kagome lattice, which is a famous lattice for its natural frustration. And then we are going to go back. What we're going to do, we're going to try to look into one-dimensional systems when you tend to think that everything was solved like 100 or 150 years ago. And I'm going to show you that's not quite true. Then I'm going to introduce twisting. I'm going to twist those lattices in a certain way. Then I'm going to free those magnets and show you that when they can move, they set certain constraints on magnetotactic bacteria. Okay, so that's the story. I'm going to go point by point. Please interrupt me when you have any question. Let's go. So model. We're going to start with the dumbbell model. What do we have here? You can buy this in some stores or online. So what you have here is the model. You have a south pole in blue, a north pole in red, and you have a magnetic bar, an axis, and you have mass. These are massive objects. standard magnet. So I characterize this by a moment of inertia, but think about rotational inertia. 2a is simple, is what you measure with a caliper from here to here, is the total distance, the length. Q is going to be something that we're going to call magnetic charge. You say, okay, but there is no such a thing like magnetic charge. Well, there is a mapping where you can use magnetic charges. It has been used to identify magnetic vortices. There are different types of charges, but there is an exact mapping. The only thing that you have to respect is that, of course, there are no free charges. The total sum must be 0. That's it. Okay? So first thing, we're going to characterize these magnets. So for people working with magnets, which there is one in the lab, you can take a universal testing machine with the magnets. Of course, you have to build some holders that are non-magnetic. These are acrylic holders, and just pull them apart. So you have two magnets, the most standard thing you do when you're a kid, and try to pull the strong magnets apart, and then you see that the force decreases. How it decreases, these points are experimental data. This is for a different type of magnet, different diameter. And the black line that you can see, you can see there, is the model considering that you have magnetic charges and they follow a law that goes as 1/distance squared, like Coulomb's law, gravity, or what we need, and you keep going. Which gap? I have 2 points here. There is a blank. I have no idea. Ah, I know. Probably my student took many points apart because it was too crowded. That's it. But good catch. Good catch. But the agreement is pretty good. If you plot them in log-log, you see that the exponent is minus 2.0001. It's really good. It's really good. So we can rationalize these magnets as two magnetic charges. It works. It works very well. So that is for the static limit. So you have the charges, but we want to characterize and understand things that are moving. Rotors, XY magnets, things that are moving around. So what do? You take a look and you hit a little bit of magnet and you measure this. That's the angular dependence. Here there is a missing point there. I don't know why. And so you just measure the dynamics. You do the standard transformation between images and data. And then the important thing is that there are three typical times. Tau b, this is immersed in a fixed magnetic field, so that defines the typical time to go forth and back, that period. Tau eta is defined by the envelope. So from there, you get the damping, so the dissipation of the system. And this is a special time that only appears when you have many magnets interacting. So imagine North Pole, they will repel each other. If they are fixed, they will rotate quickly. They will rearrange. So that is tau c. And if you look into the equations, it looks like the typical plasma relaxation time, actually. Okay. So we have Q, we have moment of inertia, we have completely characterized the system, and now we can play around. We can take all the limits. So this was done long ago in Mahadevan's lab. Somehow I convinced Professor Mahadevan to go into these frustrated lattices. We build these Y structures, this triad of magnetic rotors. So the rotors can go out of plane. They are not Heisenberg magnets for the one that have worked on that. They can move in this direction. That's it. So this can move up and down. But you see, when you have three magnets in this Y configuration, you have North Pole, they repel each other, and they have South Pole here. So that is what is called frustration. And if you think about this as magnetic charges, North Pole charge +1, -1, total charge at the vertex +1. So you have an effective magnetic charge there. So that's the lattice. It was a painful process to build this, to avoid all the experimental uncertainties, but was done. I don't remember 700 objects in there. And the nice thing is that you can measure directly spin-spin correlations because you have nice images. And we did the experiment. The system started from a polarized state. So we made a huge solenoid, put the setup inside, polarize all the magnets, and then let the system relax. And we can get the full information in this classical limit. And it relaxes, it forms a lattice with some defects, but very little defects. When you repeat this over time, it was reproducible. And the important thing is that you can measure the spin-spin correlation directly from 3D reconstruction, and you see that you get into a geometric limit here, which is universal for this lattice. And that is a result that we reported. I think I'm not certain that was one of the first articles reporting microscopic magnetic frustration. And with this simple system, we were able to capture many of the characteristics that you see in frustrated magnets, but you can poke it with your finger, you can check, you can take the classical limit, which is always good. You have a benchmark. If you know the classical limit of these things, then you have a benchmark. If you work in quantum, this is still interesting because you have a benchmark and you can understand what is going on. So this was two-dimensional on a frustrated lattice. So you'll say, okay, lattice is frustrated, that is interesting, there is geometry there is competition, there is this wide junction frustration. But let's take a look, go back into a simple problem. The simplest possible problem is just one magnet, just take a one-dimensional XY chain. So the magnets can move on the screen and change the angle. They can rotate. You characterize the geometry. That is the real experiment, by the way, without the balls that was superimposed just to show the north and south poles. And that's the model. So what do? We take all the information that we got from the calibration experiments that I showed you before, and we first ran a simulation, then did some, took the equations of motion, did some analytical work. And here is the actual solenoid. We have a very nice uniform magnetic field inside, a mirror to get the second image from the top. One image from is the lateral image. And then you just try to polarize. So you increase the current on the solenoid, and then these magnets will start moving somehow. So how? Experimental results are here. And that was also new. That was also a new result. You think in terms of one-dimensional change that was so long ago. No, we showed that that there was new information here, and it is nice to understand a one-dimensional XY chain because you can use it to design hysteresis loops. So you can. This is the building block of a magnetic metamaterial. So these are the curves that you obtain with a single chain. So the red dots are what you get with the numerical simulation when from your calibrated data and the standard model with damping. We don't take into account static friction. That's important because at the very beginning it is important. It's just pure damping. And you see that the blue dots are the experimental results. And what do we measure? That My looks like an average, but it's very simple. You have the magnet in this direction when you have the ferromagnetic state, head north-south, north-south, and they start tilting because they have an external magnetic field pointing up. They get into a canted state. And then all of a sudden, they go up, which is this configuration. So they are polarized. When they go up, this quantity, the magnetization in the y direction, saturates and goes to 1. But then you start cranking down the magnetic field. And you keep going, keep going, keep going. And then it goes down, not in the same place, hysteresis. You have a loop. You have dissipation, and you think, no, this is because of friction. That's the first thing you think. And it turns out that it's not. There are regions with different stability. And that is the second thing that I'm going to show you. We solve the equations of motion using analytic extensions. There are different types of methods. You can use symmetries, but there is a very nice a software called Auto. Now you can do in Python, any software you want, but you can get exact solutions. What is the meaning of these solutions in red? They are all polarized pointing up, but when there is no magnetic field, the x-axis is the magnetic field, this becomes unstable. So here, when you have a strong magnetic field beyond this limit, it goes stable, and then this goes unstable. And there's a saddle node here, a pitch for bifurcation. So what you see is that that's solving only three magnets with XY symmetry, simplest problem ever. You can capture the stable solutions, understand that hysteresis is not because of friction, it's because there are solutions that extend up to this point, and then you get a loop, and you have many unstable solutions. All this bunch of red lines are unstable solutions. We plot them, we classify them by different symmetries, and that is what explains, it's not friction. It's an intrinsic structure of the system with only n equals 3. With n equals 3, you have, with n equals 2, you also have hysteresis. But you may think that it's because of boundary problems. No, it is the type of solutions. The only degree of freedom is theta 1, theta 2, and theta 3. Three angles. Yeah, 3 angles. Go ahead, please. Yeah, you're completely right. Everything is simple. If they are too close, then the internal magnetic field is large. So you need a large field. You're in this area, a large field to flip them. But once they are polarized, they will go down because they just need a tiny perturbation will go down. And there, the idea of a dumbbell model is relevant because if you have point-like dipoles, you won't have the same thing. And second, you can control, well, I'll show you that. We will get over it. So this is in the case when you have half of delta, the previous slide, you have delta. Delta is the minimal distance between poles. So how close they could be, 6/5, A, and the next one is half of that. And you see that the loop, the hysteresis loop, grows enormously. These symbols are just the isotropy lattice. Is a classification for the symmetries that appear. It is well understood how to classify the symmetries here. And with that experiment, we were able to explain how hysteresis appears in the system with n equals 3, very simple. And something really cool that appeared here that first we thought it was a numerical problem, where these states that are stable, but really tiny, they live in a small region, and they become unstable. They exist. They are there. And again, you may think that 3 rotors with n equals with symmetry, with XY symmetry could be trivial. No, it's not. And then here we increase what happens when you increase the number of magnets. I call this the spaghetti plot. You obviously you get that the complexity of the magnetization in the y direction increases, but you get a bunch of new configurations. You see here one that looks stable. Look, what is that in a one-dimensional magnet? That is something that resembles a domain wall. So in this system with n equals 6, I'm sorry, you get way more complex solutions that are now stable. You get hysteresis loops that are way more complex. And this solution, for example, you see red, blue, then blue, red. This is a domain wall. It's a head-to-head domain wall that people have used, for example, in racetrack memories. And you can see that here, and you can manipulate. So n equals 6 is interesting, and you can really understand what is going on with an extremely simple system, XY symmetry. And why do we care about unstable solutions? Well, because there is something. Go ahead. Sure. There. How does it pick which one to go? One represents that only the boundaries are moving, and one that the something in the center is moving, or off center, but not the boundaries. That actually that was part of the discussion with the referees. So why unstable solutions, all this bunch of solutions that are in red are relevant? Because you have, so essentially I'm working here because I have a feedback loop, because my stable solution is to be facing the ground. My center of gravity is here, it wants to be there. So this is an example of a Kapitsa pendulum that you can stabilize these solutions by some type of perturbation. And this is a standard demonstration that an inverted pendulum, it is stable, and you can search for those unstable solutions by magnetic forcing with an alternate magnetic field. And we have done that, and we found a bunch of solutions that are look like little porcupines. We haven't classified them, so if you're interested, I'm more than happy to explain you how to build a system. It's super simple. So, and then the twist. You go and take the twist. So this is not artificial intelligence. This is the real 3D printed. These are like forks. These are the magnets, 1 centimeter, 0.5 in length. They are hinged, so essentially they are like a hinge, so they move in this direction. So this is, you classify the angle here, theta, and the angle of this plane is going to be phi. You have n of such rotors that move only in one direction. But if you are the rotor, I'm moving this, it's going to be your alpha, but someone will change your phi. So I could go this direction. So that is my control variable, phi. So why is this important? Well, first, probably you have here that on graphene, there is a lot of work doing twisting by layers. And if you take a single layer of graphene, you pull a little bit, you distort the lattice, then you get pseudo-magnetic electromagnetic fields that could, the pseudo-magnetic fields could be huge. And with this, again, this is one-dimensional, but we increase the complexity in 1 degree of freedom. We can all twist together, and what we get is the solutions. Incredibly simple. Ferromagnetic, what we learn in school, north-south, north-south, north-south. But once you twist this plane, you can get like a Pickering angle. And if you twist a little further, you get anti-ferromagnetic order. So continuously, you go from ferromagnetic order to anti-ferromagnetic. I'm not going to discuss the system when it's forced, but it has very nice nonlinear dynamics. So it's really, really interesting. And furthermore, during the 50s, when the first paper of NMR appeared, there was this angle that was, they call it the magic angle, when you rotate the sample, and they get that for this angle that was like 54 degrees, the sample gave the maximum intensity to measure. It turns out that the angle where this transition happens from ferromagnetic to anti-ferromagnetic order is the same.
So after who that magic angle is named?
I don't know.
The Love magic angle, named after Irving Love. He taught me classical mechanics.
Oh, nice. Well, that's the magic angle. I have to include that anecdotal thing in the presentation. So this is simple, low budget, but it's very rich. So, and then something that probably Professor Bandy will like, there are a couple of works, important works about Hofstadter butterflies. and how they appear in the spectrum because they are solution of a Harper type equation. Then this was worked out to be important because there are some Chern numbers that are special here. And then the ambitious question, can we get something like this with our macromagnets? Can we? It seems too ambitious, but there we go. I'm not saying that this is Hofstadter butterfly, but when you consider a small modulation in the angle phi, this is with a tiny amplitude, epsilon is 0.3 here, have 100 magnets, and starting from a ground state that is ferromagnetic, so your phi 0 is 0.2, if you modulate the angle of the plane, and you compute all the frequency for small oscillations, so the frequency of the excitations, and you sample many times as a function of this psi variable, which is what generates the modulation. You plot the eigenvalues, and you get this structure that is, at least to me, surprising. And then you can go into the other limit. Remember, the ground state is ferromagnetic. Now we go into the ground state that is anti-ferromagnetic, the same thing. So student is working on a solution for this, but even the numerical spectrum is appealing, at least. So very simple system, only you have a tilting angle and modulate that tilted angle. And it's periodic. It's periodic in the, there is a super lattice, but it's periodic. Go ahead, please. It looks like yes. Yeah. Yeah, yeah. So if you, given that you asked the question, I'm thinking, okay, we have a study with Paula Mellado, that is my long-term collaborator. We have studied magnetic clusters, all type of things. She's on the quantum side, but there are some molecules that could work as altitudinal rotors. So if someone could measure this, they could have gap states that modify the spectrum at will just by changing one specific variable. Yeah. So what are the bacteria? So let me see. Sure, please. Yeah. You're right. Yeah. As far as I understand, it looks like there are also some shoulders here that explain why the numerics has the experiment somehow has less dissipation than the model. That's a good question. The thing is that when you compute the time for the damping time, the most likely thing is that in the numerical model, when they interact, when they are too close, the force is too large. So I think that that's the problem. So you're inducing a problem there. I don't believe in this shoulder, for example. It appears here, but I don't know what is the real origin. Yeah, yeah. I didn't show you this here, but if you take a line, this is a chain. This is only the chain, okay? But if you build a T, the basic extension, one-dimensional chain here, one-dimensional chain here, then you can change all the structure and get a huge hysteresis loop at the center at 0, 0. So yeah, that's a very good question. We didn't care that much at that time, but it's a very good question. Thanks.
In your hysteresis curve,
Sorry.
the experimental curve has lesser area than the model. I would have expected the reverse, where you have some
Yeah,
friction-induced dissipation also added.
Yeah.
That's counterintuitive.
It's counterintuitive. There could be different sources. There could be one source when you calibrate for the damping, maybe some magnets, because remember, this is mechanical, it's dirt. Some of them could have more damping, some less. This is not in, yeah. That's another possibility. But the honest answer is, I don't know. Go ahead, please.
Very good. Can you make closed boundary conditions?
I can share with you an article when we did a close boundary conditions. Yes.
Does this diagram change?
Yes, and it depends on a. This is funny because it depends. There is an odd-even effect. You have a number of odd magnets in your loop. You cannot close. So you have perfect in the ferromagnetic state. You have a vortex state that was reported long ago in nanorings. But if you change the angle phi, for example, for the next for the twist, then you get something that contains a block domain wall. If it is even, if it is odd, you can close that. So yeah, these things are plenty of information and physics that you can explore playing, as is the title. Kapitsa, there is a twisting model. And then this thing that is in exploration. There are some limits that we have. There are a lot of tools to work this in an analytic way, but I think that is something appealing. So where are the bacteria? Because also bacteria is everywhere, or mouth is here. But in the last part, in the last half or last 20 minutes, I'm going to show you quickly how do we apply this dumbbell model, this idea that for classical magnetism on bacteria. So I call it this Magnetotactic 101. It's pretty fast. So Richard Blackmore reported this bacteria that is able to sense magnetic field that is called magnetotaxis. However, then Richard Frankel found this article by Bellini when he reported 13 years before sensibility to magnetic field. So this is the real discoverer. Richard Blackmore was rediscovered this, and this happened because it wasn't in the. I guess it wasn't published in the right journal. That's a way to say. But let's make some justice. He was the one that discovered this bacteria. So imagine that somehow you're an organism and you have a magnetic compass inside you. So if there is a magnetic field pointing that way, you go that way. If someone changes the magnetic field, you go that way. So what this bacteria does is uses the Earth's magnetic field, to follow certain directions for localization. And how they do that, they have these organelles that are called magnetosomes. Magnetosomes are essentially little chemical reactors that can produce the magnetic nanoparticles. That's it. Yeah, Grigerit or ferrite, yeah. And this is an holographic image. It's fantastic. You can see the nanoparticles there. And they're using nanodiamonds, NV centers. It was possible to measure the stray field of these magnetotactic bacteria at the scale of nanometers. So, and you see that it is a magnet. You have the magnetic field. You can do that with current technology. To me, this is fantastic because I clearly see that this is compared with the size of the bacteria. The chain is not a point-like dipole. The length scale is comparable with the size of the bacteria. And this is a reconstruction in the C direction that you see all the nanoparticles that are ferrite, they're all magnetic, so you can see them. So there is an organism that inside of its body has a magnetic compass. And that's the way it is. And the length scales are here. We obtain these length scales from different literature. You can use something similar to Hahn-Bohm effect, like electronic microscopy, using the phases to look into the magnetic structure of magnetotactic bacteria. It's called electron holography. And why is that? Why they use this? So it's an adaptation, like most adaptations in nature. They tend to live in areas that they have some very specific amount of oxygen, really little. They tend to be anaerobic or microanaerobic. Why? Because oxygen is toxic for them and for most organisms, not for us because we have blood and we have a way to get rid of what occurs with our metabolism. So the Earth's magnetic field is everywhere. So here you have a diagram with the stray field of this huge dipole. So in few words, helps magnetotactic bacteria to search for the right place, to go into the sweet spot when they have food, when they have the right amount of oxygen. So given that this is a lecture, pop quiz. Okay? If the red arrow indicates the velocity, of course, there is a flagella here, there are more details, but imagine that this is the velocity, the instantaneous velocity. And here the magnetic chain is a compass that is pointing up. It is trying to get aligned with the Earth's magnetic field. And in this case, the compass is pointing down. Which one will survive? Remember, up here, you have oxygen, toxic. Yeah, it has to go down. There are many details. Actually, this is a field where people are studying how they move the flagella in terms of, so there is some chemotactic mechanism, but the one that goes opposite to magnetic field. So they want to go deep and then get into the right spot with low oxygen. And that's the adaptation. They need to align with the magnetic field. Questions? So here you have an example of what is going on with this. There you have the magnetotactic bacteria, and someone took from the lab a magnet, and you can see that huge clump of bacteria, poor organism. But that magnet is just too strong, these guys. So it is magnetic, it's really magnetic. And then this magnetococci, this is special, this magnetotactic bacteria, because they have a main compass, but they also have many magnetosomes around. So it's not the same type of arrangement of magnetic compass. And then they go back to the boundary where they have their food. So the model, we're going to apply the model for this bacteria. So here you have the magnetic field that has been measured with MV centers. So the model that we're going to use is a particle that looks like a stadium, positive magnetic charge, negative magnetic charge. The magnitude of Q depends on the nanocrystal magnetization and dimensions. That is well known because it depends on the material. And all what we're going to use is this calibration that we mechanically did. So we demonstrated that Coulomb's law is valid for magnetic materials. And we're going to use this dumbbell model all together with a magnetic interaction in terms of north poles, positive magnetic charges, and south poles, negative magnetic charges. This Coulombic model. And of course, these organisms move. So we have to take the first limit. The first question, the first important question is, how many of these nanocrystals do we need to generate an alignment, given that this organism is living and it's living in a thermal equilibrium? So it has a Brownian motion. So in few words, what you do is you equal the thermal energy with the magnetic energy. When that occurs, then you get a bias. So it is oscillating with Brownian motion. It also has some nonlinear motion because of the flagella working. But this estimate gives a minimum of 10 nanocrystals. So okay, we have the lowest bound for the size of this chain. But the question is, if you think about it, maybe to have another crystal and another crystal is better because it allows you to align faster, larger torque. So that's the question. What is the upper bound? It is needed. So lower bound is given by the scaling between thermal energy and magnetic energy, and upper bound we don't know. So the physical mimicry we're playing, this is a toy, it's called an X-bag, that we cover with this stadium-shaped 3D printed structure. The variables are there. That's a magnet, a neodymium magnet that was calibrated beforehand. And the model is this. So we have interactions, some director vectors, and so on and so forth. So this is what we call active matter. I know that it's a field that is a bit controversial because there are some pros and cons, but okay, this is what it is. Bacteria move, is active. And we determine in terms of these two dimensionless parameters. This is a diagram. If you want to look into the full numerical simulations, you're welcome to ask me. But what does it mean, alpha? Alpha, imagine that it depends on the velocity of the organism. So you increase the velocity, this axis goes up. What is the meaning of beta? Beta is the competition between rotational torque and Coulombic torque. So you have oscillations in the angle, they move because they have the flagella moving all around. So you have the torque that is due to rotational noise and the Coulombic torque. So if you have too much noise, you walk in this direction to larger B. So if you have too much noise in the angle, then the particles will never be together, they will be free. If you have less torque and less velocity, they will tend to form clusters. I call DI because typically in experiments they form dimers. If you have low beta, so low angular noise, and moderate alpha, moderate velocity, you form ferromagnetic chains. If you keep going down, you form a vortex state, and here you form a canted antiferromagnetic state. And in the blue, the particles have zero velocity, so you have just an XY model, two-dimensional XY model in random positions. So we did experiments. All the phases shown in the phase diagram have been confirmed. So let's do the experiment. The free phase, they move around. They have certain velocity that we calibrate by charging the batteries, waiting some time. Second phase, dimer. So the strength of the magnet is a little bit larger, and the magnet is a little bit shorter. And you go into a system that has translation. Then they couple together, and they go, let's say, from a state P to a state S. They just keep turning around. Ferromagnetic phase, the magnets are a little bit larger, so they tend to form chains. They collide. This is a high density. There was one that is slower, so there is a little bit of noise, but they form chains. The vortex phase, that was my hand. So they can form a vortex. There is a confinement, of course. These are inertial objects. It's not like low Reynolds system. There is inertia. So they form a big vortex, stable. And to show you that this vortex phase is stable, you can see this. Again, I think that these are not my hands, somewhere else. Take a dimer and collide it with the vortex. They hit each other, they fight for space, and then you get fusion. You get a larger vortex. Okay? All the phases you can measure. The important thing in these things there are no free parameters, because we're going to now run the numerical model, the model with dumbbells and Newton's laws and all that. First one is just shape and isotropy, and they get clamped in one boundary. Second one, you go into a larger magnetic interaction, and they tend to form vortices. Exactly what you observe. And a big vortex. We have seen these phases. It's kind of funny. So using that calibrated model, we're going to ask the question, what is the upper bound for magnetotactic bacteria? So we took all the parameters measured by different groups, and we call the charge 1 for the magnetotactic strain 1, that is a magnetotactic spirillum. It is quantified. People have measured with all these techniques of holographic measurements. NV centers have measured the size of the magnetic chain. They have extracted the nanoparticles, measured the magnetization, all that. So with those quantities and with the typical length scale of this magnetotactic strain, magnetotactic bacteria, we run a simulation. No approximations, and they move. They're happy, and actually they look quite alike how they look under the microscope. If you remember the magnetococci, they look very similar. And this is a model. The only approximation is the geometry, is the stadium shape. But what happens if you increase the magnetic charge? If we increase the strength of the internal magnetic field? There was 1. So 1, 4. Look what happens when we go up to 4. You see these tiny clusters? You see certain type of order is emerging. And if we go up to 10, look what is going to happen. And tell me if the average velocity of those clusters increase or not. So somehow, if you have a magnetic strength, so if the number of nanocrystals increase, or you increase the size of these crystals, magnetotactic bacteria will get into a state when they form clusters, and that is detrimental for their locomotion. So they cannot move. These guys won't survive. They don't have any way to move around. So some quantification of this, and what we see is that as you increase the charge in the system, you see everything in ferromagnetic state, and for some critical charge in units of 10 to the minus 10, that is the typical charge for an actual magnetotactic bacteria. Right here, you go into an order where one bacterium is pointing that direction, the other is pointing this direction. They form clusters, and they cannot move anymore, like the dimer phase that we observed with the macroscopic experiments. So there there is a physical constraint where even though the magnetic compass that is inside of that organism enhances the ability to survive, if it grows too much, then your ability to survive goes down. So that's it, summary. New phenomena using extremely simple models, very, very simple experiments. Something that I really like is you have classical benchmarks for magnetism. Take the classical limit is always good, and if you can see and touch it, it's even better. One-dimensional chains are worth exploring. They have many, many interesting structures. Twisting allows very simple control. This is a geometrical knob that hasn't been explored apart from the twisting by layers. Even in one dimension, it is quite interesting. So magnetism geometry set an upper limit for the size of the magnetosome for magnetotactic bacteria. And this nice model generates a consequence that magnetic self-assembly can be predicted and maybe controlled. And that's it. I have to thank my students and former students. I have a picture. Mariana, that did her thesis on informatics on this subject, very patient person. Santiago working really well. Thomas Hibb, Alexandra working very well. Joaquin, he really loves to do things with his hands, working in the lab. Macarena, she just graduated from Liverpool. Javier just graduated from his Ph.D. and having a good time in the south of Chile.
Questions, comments?
So, still the last part of this talk about the bacteria and all these motor reactions driven by this internal magnetic compass and all. But I still believe that the direct influence of this magnetic compass to their locomotive actions, it's for me, it's like I can't imagine it because usually organism like they sense something and then they
React.
react.
Yeah.
But what you are saying, or you are trying to model it like that, there is a direct interaction, and because of that, all of this.
Yeah,
emergent
as you
properties-
increase the let's say the size of this magnetic chain, or you increase the magnetization, changing the material by doping, by doing something, some magic with genetics. That's what I'm expecting biologists to do. So you could perfectly go into this regime where you cannot move anymore. And there are many details. I know how flagella moves. Also, the shape is not a perfect stadium, but there's a nice experiment in which people have done the following. They take, imagine your here is moving in that direction, and people put a magnetic field, and then that is out of plane, and you clearly see that it's making U-turns. So the magnetic field is important, and the compass is important. You see why it is?
Yeah.
Did you do these simulations with a bias field? How does that affect the overall behavior?
What do you mean with the bias field?
As in an external gradient?
We did both. We did considering the Earth's magnetic field. We did it considering that you're in the equator, so no magnetic field. We did and the effect of this transition between ferromagnetic order for bacteria and antiferromagnetic is robust, oscillates a little. Yeah. No. Great question.
I have two questions. Maybe they are too basic and too naive. The first question is, how is gravity affecting the bacteria? And if you make experiments changing the gravity and how they reorient, even though they have these sensors, magnetic sensors? And the second question is a little bit more biological, and maybe like what you think about certain cells, for instance, cancer cells, to have produce some kind of alignment towards a clustering. Do you think there could be any kind of phenomenon related in those cells?
Those questions are anything but innocent. They are very important. For the gravity, there have been experiments, inconclusive, in the space station. A group during the 2005, they did measurements with magnetotactic bacteria. The first intuition is they're buoyant, so they live in water, so gravity doesn't matter. I'm not so sure. So no clear answer for your first question. I don't know. For the second, there is a little deviation from your question, but I don't know if cancer cells do cluster using a similar mechanism, because I don't know if but probably there is a protein and they cluster. It could be like the effective idea could be, but what I do know is that people is taking this, and this is a hot field now, is taking is taking these nanocrystals. They're trying to enhance the production from some strain of this bacteria, control them, extract them, put some glue on top, some proteins, inject them, then they go directly into tumors, and then they put the person in an alternating magnetic field. And they use the hysteresis loop to do hyperthermia. So to essentially burn tumors. So, and that is a hot topic now in biology, in the translational medicine. Yeah. Thanks for your question. Go ahead.
Okay. So three very quick questions. So Kagome lattice is two-dimensional frustrated lattice. Its three-dimensional analog is pyrochlore lattice, which is corner-sharing tetrahedra. Have you looked at the 3D versions of how those spins behave and what they do?
Great question. If you go back, I think that we were kind of in this system. We published this in this article. You go to the supplementary information, and we did a three-dimensional thing with a pyrochlore lattice. I never published. You said, no, this is just a detail, just not worth. We didn't know the field in detail. We were just starting looking into this simple system, and now there's a really great article that appeared like 15 days ago. You take one lattice, the same thing, another lattice, even with simpler symmetries, and then you produce shear between lattices, and you can control friction. And you violate this Amhor law. What is this? The standard laws of friction. Ampere.
Second quick question. So you mentioned
Ampton.
You mentioned about monopoles. The spin ice, you have monopoles.
Yeah.
Monopoles can move. Yeah. So that's called magnetricity, like electricity
Yeah.
and magnetricity. Have you looked at moving monopoles, effective monopoles, and creating magnetricity?
We have seen, we haven't controlled, but what we can move, and there is a student that actually is now in Japan. I don't know where he is, but he's in Tokyo. What you can do is take these one-dimensional chains, let's say, I don't know, 40 magnets, and one of the stable states, now when you have large N, is a domain wall, a charge +2. And you can move it in like racetrack memories. And there is something more interesting that Oleg Tretyakov, at some point, he predicted resonant motion in ferromagnetic films. We have observed that. We haven't reported that just because the student was the typical thing. If a student is doing a great job, he will move quickly to the next job. So you can put an alternate magnetic field here, alternate ACB, and you can, given that this have inertia, you can excite and generate a resonant mechanism and move it forth and back. You can.
And finally, the migratory birds use Earth's magnetic field. They go north and south.
Yeah.
They have some magnetic stuff there. So is the mechanism similar or something else? I don't know.
The what?
The migratory birds, they sense Earth's magnetic field. They actually sense latitude.
You know,
angle.
I know, but I'm not up to date with magnetic birds. Some people have reported that they have a protein that is able to do that. To me, all the demonstrations are inconclusive, but I don't know, maybe there is something new. I don't know.
Because there were also reports about magnetotactic ants that build termite mounds that are knife edges pointing north and south, and therefore they're they have magnetic. They do it because of the sun, east to west, not north to south. So
the birds I learned somewhere that it's not the magnitude of the magnetic, it's the angle. So that's the latitude. They can sense latitude.
really they have a lot of latitude.
I think that the most appealing hypothesis is this of the radical pair that Klaus von Schulten from Illinois, he proposed the mechanism long ago, and the mechanism makes sense. But I don't know if there is like smoking an experiment. I don't know.
Any other questions, comments? Andres is here until May 2nd.
Yeah.
He hangs out in our lab. He's in the TSVP area. If you're interested, he has very broad interests. So his interests span from the cosmological to the quantum. So please feel free to drop by and have a chat with him. Thank you very much. Let's thank Andrés.
Thank you.